Hello again, my physics students. This is Mrs. Buchanan, and this is flip video number 9. We will continue our discussion of Newton's second law of motion, force and acceleration. But before we do that, let's revisit our big idea. An object accelerates when a net force acts on it. We will be discussing learning objective number 4 today. And learning objective number 4 is discuss the relationship between acceleration and mass. I want to take a couple minutes here and I want to talk about some common misconceptions about forces. And there are 5. The world is dominated by friction, and so Newton's ideal friction-free world is not easy to visualize. In addition, many terms used in physics have everyday meanings that are very different from those that we understand in physics. Here are some examples of common but mistaken ideas about forces. Number 1. When a ball has been thrown, the force of the hand that threw it remains on it. No. The force of the hand is a contact force. Therefore, once contact is broken, the force is no longer exerted. Misconception number 2. A force is needed to keep an object moving. If there is no net force, then the object keeps moving with unchanged velocity. If friction is a factor, then there is a net force and the object's velocity will change. Misconception number 3. Inertia is a force. Well, we know inertia is the tendency of an object to resist changing its velocity. Forces are exerted on objects by the environment. They are not properties of objects. Misconception number 4. Air does not exert a force. Well, air does exert a huge force, but because it is balanced on all sides, it usually exerts no net force unless an object is moving. You can experience this force only if you remove the air from one side. For example, when you stick a suction cup on a wall or table, you remove air from one side. The suction cup is difficult to remove because of the large unbalanced force of the air on the other side. And misconception number 5. The quantity ma is a force. No, the equal sign in F equal ma does not define ma as a force. Rather, the equal sign means that experiments have shown that the two sides of the equation are equal. So we're going to talk a little bit about using Newton's second law before we get into it. Newton's second law describes the connection between the net force exerted on an object and its acceleration. And if we go back to our Getting Pushy lab, you saw this in action. The second law identifies the cause of a change in velocity and the resulting displacement. Newton called this a law of nature because he thought it held true for all motions. Early in the 20th century, more than 200 years after Newton's time, physicists discovered that the second law is not true for velocities close to the speed of light, nor for objects the size of atoms. Nevertheless, all of our everyday experiences are governed by this physical law, which was formulated over 300 years ago. Aristotle's followers believe that the heavier an object is, the faster it falls. And we talked about this and watched our video with the astronauts dropping a feather and a coin. So, doesn't the coin fall faster? You can see for yourself that the evidence seems to be in Aristotle's favor. But Galileo knew that if he was to understand the nature of the force that causes an object to fall, he had to simulate an idealized world in which there is no air drag. You also did this with your coffee filters. So let's talk a little bit about mass and weight. While there is no evidence that Galileo actually dropped 2 balls from the Leaning Tower of Pisa to test his ideas, he did describe the following thought experiment. Two cannonballs of equal weight dropped side by side should fall at an equal rate. But what happens if the cannonballs are tied together? Now, according to Aristotle, they should fall twice as fast. But Galileo hypothesized that all objects, no matter what their weight, gain speed at the same time, which means that they have the same downward acceleration. This hypothesis has been tested and found to be true. What is the weight force F sub g exerted on an object of mass m? Galileo's hypothesis and Newton's second law can answer this question. Let's think about a falling ball in midair. Because it is touching nothing and air resistance can be neglected, there are no contact forces on it, only F sub g. The ball's acceleration is g. Newton's second law then becomes F sub g equals mg. Both the force and the acceleration are downward. The magnitude of an object's weight is equal to its mass times the acceleration it would have if it were falling freely. This result is true on Earth as well as any other planet, although the magnitude of g will be different on other planets. Future astronauts will find that their weights vary from planet to planet, but their masses will not change. Let's think about that bathroom scales. What's being measured, mass or weight? A bathroom scale contains springs. When you step on the scale exerts an upward force on you. You are not accelerating. The net force is zero. Therefore, the magnitude of the spring force, F S sub SP, is equal to your weight, F sub G. A spring scale therefore measures weight, not mass. If you were on a different planet, the compression of the spring would be different and consequently the scale's reading would be different. So we're going to talk a little bit about how to problem solve when we look at Newton's laws. And I'm going to give you 8 things that you should think about. Number 1, read the problem carefully. Visualize the situation and create the pictorial model with a sketch. Number 2, circle the system and choose a coordinate system. Number 3, decide which quantities are known and which quantity you need to find. Assign symbols to the known and the unknown quantity. Number 4, create the physical model, which includes a motion diagram showing the direction of the acceleration and a free body diagram which includes the net force. Number 5, to calculate your answer, use Newton's laws to link acceleration and net force. Number 6, rearrange the equation to solve for the unknown quantity, A or F sub net. Newton's second law involves vectors, so the equation must be solved separately in the x and y directions. Number 7, substitute the known quantities with their units in the equation and solve. And number 8, check your results to see if they're reasonable. So let's get back to our learning target and let's talk just a little bit about how mass resists acceleration. And again, we are going back to lab number 8, which was getting pushy. Push an empty shopping cart and then push equally hard on a heavily loaded shopping cart. The loaded shopping cart will accelerate much less than the empty shopping cart. Acceleration depends on the mass being pushed. For a constant force, an increase in the mass will result in a decrease in the acceleration. The same force applied to twice as much mass results in only half the acceleration. For 3 times the mass, 1/3 the acceleration results. In other words, for a given force, the acceleration produced is inversely proportional to the mass. This relationship is written as an equation: acceleration is proportional to 1 over mass. Now remember from your vocabulary, inversely means that the two values change in opposite directions. So mathematically, we'll see that as the denominator increases, the whole quantity decreases by the same factor. So let me leave you with a question. How does an increase in mass affect acceleration? Thank you.